Hi, everyone. So for my final project, I decided to take a look at this cool new theory where they incorporate viscosity into a cosmology model. So I'm just going to really quickly, in 5 minutes, describe all like the major points of that, but you're welcome to pause the video, check out the slides, or ask me any questions. So to start off, we use the cosmological principle. So we consider the universe an isotropic fluid on a big enough scale. We set these constants to be 1, and we said the universe is spatially flat, which is what we observe. Basically, what you have is the mass, energy, momentum, all that kind of stuff is contained in the stress energy tensor T here and GR in cosmology. And so for a perfect fluid in equilibrium, here's the form. P is pressure, rho is density, U is the floor velocity, and then G is the space-time metric. So specifically, it's bulk viscosity that we're talking about because for the space-time metric, that's pretty much the standard in cosmology. Bulk viscosity is the only type that actually makes a contribution. But in this like original paper from Eckert, it's the same form for T, except now you have this additional term with the zeta being a viscosity coefficient, depends on these, and then it comes from the divergence of the floor velocity. So the problem with this theory is basically that you can get superluminal signals, which obviously doesn't make it physical because that violates relativity, so we need a new theory. So this new one from 2015 from these scientists at Vanderbilt, they make a slight modification where they say it comes from the divergence of a dynamic floor velocity, which I call C. Basically what they do is there's a fluid index F that depends on what type of fluid it is and the equation of state. And it's basically just like a 1/c² relativistic correction for when you consider viscosity. It's also physically motivated. Here's the form here, where mu is this rest mass density, which is the density that we consider in this class. But anyways, they changed it so that it's the form here, where the only change is now it's this dynamic fluid floor velocity. So cosmological equations of state, you have the parameter W, here's what the form it takes. And so for the scale factor A, which is basically the size of the universe, that's the x-axis on this graph here. Here's the forms for the different types of matter, energy, whatever you want to call it. But I'm going to focus on dark energy, and we think W is -1 and that it's a cosmological constant, so it doesn't depend on the scale factor. So this theory, you can do a bunch of math, and I'm going to skip because I don't have time, but you get to an effective W that depends on all this, where mu naught is the rest mass density today, and then H is the Hubble parameter. But with this theory, you find that there's some special results. If you have the case where it's pure dark energy, so W is -1, or if you have a stiff fluid, which basically means like the relativistic version of an incompressible fluid, you find that the effective W is the exact same, which means that the viscosity doesn't matter at all for those cases, which is pretty interesting. But we also want to get to a functional form. We want density as a function of scale factor, and here's the equation you can use to do that. So if you go through a lot more than I'm going to skip, you get to this kind of scary looking equation that's actually not that complicated, but here's how it depends on all these things I've been talking about. You have zeta being a power law in density, which is kind of the standard assumption that people make. And it's this power law alpha, where alpha is usually a negative number for any physical system. But some of the main results for this theory are that the density actually decreases more slowly with the viscosity model than it would if viscosity were not included, which makes sense physically. But the more interesting result is that actually this model allows for a crossover from small negative W to negative less than -1. And so they think that with enough time that crossover occurs, and then the W effective will go to -infinity, which leads rho to go to infinity. So the prediction here is that in enough time, you'll get this, what they call phantom energy, or a big rip into the universe, where basically everything just kind of gets infinitely far apart, and it's kind of like a singularity for every particle, which is crazy. But yeah. So here's a plot I made where I set W to be -0.99 because dark energy today dominates, but it's not the only thing, so not quite -1. But what you see is that the density decreases up until today, which we expect. But then in enough time, you see that the W effective does cross over to less than -1, and the density diverges. So showing this big rip into the universe. So in conclusion, some strengths of this theory, it's basically a lot of it. It makes sense physically in pretty much any way you can just consider. It describes dark energy in the ways I've been talking about, and it's actually much simpler than this other theory, which is here if you're interested, but this other theory is kind of contrived and way more complicated. So this one has a lot of advantages. The only real weakness is that it does predict this phantom energy and big rip into the universe, which a lot of people discredit. But given the Planck collaboration results from 2018, Here's what we think the dark energy parameter is. So it's actually not that crazy. They predict it might be less than -1. So not that outrageous. Maybe they're onto something. And that's going to do it. So thanks.